tonight we have a very special talk. Our speaker is a PhD candidate and research assistant at Waseda University in, I don't want to get this wrong, the High Energy Astrophysics Group in the Department of Physics. His main focus is neutrino oscillations in core collapse supernovae. Does anyone know what that means? No. Maybe we'll find out. I think it means he's a very smart guy. So tonight, here to present the story of physics, we have Milad Delfan Azari.
Thank you. Good afternoon, everyone. First of all, I'd like to thank you all for coming to this event today. And of course, I'd like to thank the organizers for inviting me to talk. Actually, I don't want to name this event as a talk. I mainly want to talk about physics, and mainly I'd like to say it's a discussion. So you're always welcome to ask me questions, and definitely I will ask you questions again. But the concept of physics actually might be unknown for many of you guys. So today the title is The Story of Physics. All of us know what's the meaning of story, but I want to ask you, what is physics? Who knows? Just feel free to answer. Everything. Okay.
Science. Say it a little bit louder. I heard science,
please.
space. What else? Yeah.
Stuff.
Stone?
Stuff.
Stuff? Okay. Okay. So let me explain you in this way. Physics is a Greek word actually coming from physic or physica, which means the nature. And physics means a branch of science that deals with the nature and tries to understand how our universe and our nature behaves. This is the meaning of physics. So let me give you a brief introduction of physics nowadays, and then I'll be back to the starting point, and I will tell you how this knowledge came from, and actually what's the origin of our knowledge. Nowadays, physics is just a normal topic in middle school maybe and in university, and all of you have heard about it a lot. And mainly many of the students are having problem with this topic because it requires like mathematics and complicated equations that we have to deal with. But honestly, I think it's not that difficult, because if you understand the language of physics, then everything is going to be easy for us. So today I'm trying to explain that language to you. Nowadays, we have two different branches of physics which we call theoretical and experimental physics, which I got this question from you, that what's theoretical physics and actually what's experimental physics? I just can say, physics is a natural science, is a branch of natural science that whenever we say a physical law has been confirmed, the theory and the experiment should get the same result. Otherwise, we don't call it, it's approved. In astronomy and astrophysics, instead of experiment, what we do observations. It means that what we are doing, theory means what we are doing with a pencil and a pen, and we are trying to solve the formulas, and we get a result, a specific result. But in experiment, of course, again, we are trying to make some experiments about the same problem, and if what we see and what we are writing in our calculation are the same, then we say that's been approved. For example, even the Big Bang, all of us have heard this name, Big Bang theory. It's just a theory. It's not still proved in physics. Physics society is not accepting that, actually. So, if I want to go back to history, I'd say even our ancestors, or imagine now we are not living in 2018 and we are living in a cave, actually. So the cavemen, I believe that they were using physics too. but they didn't know that they're using physics. I want to ask you a question. Do you know how they were using physics?
So someone living in a cave
Yeah,
and how they're using physics.
yeah. Definitely they were doing. But they didn't know that they were doing physics. Okay, just when they just want to go out and hunt, right? The arrow, and how to put that arrow to that animal. That's physics. And what metal that they're supposed to use to be able to kill that specific, animal or something. Using the specific metal is physics. And after that, I can say that physics, itself has been born from the time of Greeks. Greek people were the first ever people that tried to explain the laws of nature. And all of us know that Greece has produced many great scholars, right? Like, for example, Pythagoras. And if you know that, I think now 5th grade students, right? The minimum, the grade that students are here, 5th grade. Have you heard about Pythagoras' formula? Still, we are using it in mathematics. It's not that difficult. I'll just explain later. Pythagoras was a person that lived between 582 to 497 BC. And he conducted experiments in harmony. He was just using some strings in harmony in order of, for example, 1 and 2. And by playing with them, he could make a pleasant sound. But he knew that if the order is just high, like, for example, 500 to 501, the sound is not going to be pleasant. And he did a great equation. We call this a right angle. It means that we have a 90-degree angle here. And we will call this leg as hypotenuse. So the square of C is equal to the square of A plus the square of B. That's a very famous equation that still we are using in our daily calculations. And it's going to help us a lot to understand even the nature. After him, Zeno was another great Greek thinker. He was living 490 to 430 BC, and he nearly proved that the motion is impossible. Can you imagine that motion is impossible? And by philosophical facts, he was trying to prove it. And actually he did at that time. And he tried to convince people, actually. I just can give you an example. Imagine I'm supposed to go from here to that wall. And the distance is just x, for example. If I want to go to this wall, I have to just come across here to reach this wall. Okay, so imagine just the distance is just like, 1 meter or 2 meter. Of course, it's more than 1 or 2, so 3 or 4 meters. So by reaching to that wall, what I have to do, firstly I have to come to the half of the length, right? Half of the distance. Just if it's like 4 meters, I have to come to 2 meters first. And then, from here to that place, again, I have to come to the half of it. Half, half, half. And these halves are not going to get end. So it means that I never can reach to that. It means motion is impossible. In his idea. And then, I think nowadays still it's working by, the students are trying to reach the spring break or summer break, but they're trying their best, but still, they're thinking that, long time or a long distance is still remaining. I will talk about this paradox with this guy. He tried to resolve that paradox by saying that the matter is not infinitely divisible. He was the first person that was saying that the matter is made by atoms. And he was saying that the Zeno's paradox is not correct. It's okay. It's not correct because if we are going to think like that, the person should be infinitely small. I mean, when I'm just going to reach to that wall, my size should be smaller and smaller and smaller. I mean, that distance that compared to my size should be smaller and smaller. So it's not possible for us. So that theorem was just declined by him. And probably one of the most famous guys was Aristotle. He was the tutor of great Alexander. And while great Alexander was trying to expand his empire, he was trying to expand his empire of knowledge. And he was lecturing for people based on logic, and he was talking about biology and physics. And he was the first person who named this subject physics. But unfortunately, many of his ideas were wrong. And he was believing that our planet is the center of the universe. Or the geocentric universe, he was thinking. After him, Archimedes came between 287 to 212 BC, and probably he was one of the great physicists of Greece. And still some of his works are applicable still even nowadays. And we call it professionally as his principles, that the body loses weight when it's immersed in water. Do you know what is the application of this theorem?
Go for it.
Yeah, please.
I think I've heard that the body
Yeah.
is lighter compared to water.
Yeah.
So I think that's what.
Yeah, it could be. It could be. But it has even military applications. You just can easily just launch a ship in sea, and we know that ships are really massive and they're so heavy. But when we put on a specific amount of water, so we can ride ships then. Right. And his famous Eureka, that when he was in bathroom, after that he could just get that. And one of his greatest ideas was in aesthetics also. And I intentionally put this in my class because it's so old notes. And imagine, I think all of you just played this game, Seesaw, right? Steve, maybe you are just doing it. But he was thinking that if this is F is coming by force and this is a base, and then the the ratio of F over W is equal to the ratio of this length, which is B, over A. This is still the principles of statics. And he was thinking that if he has a very long rod, he even can maybe move the planet. The next guy who did a good job in physics was Ptolemy. And he believed that the universe is concentric. And our Earth is the center of our universe again. His model was looking like this. Can you imagine? Sun is orbiting around our planet. He also did many studies in optics, the process of refraction, and did many experiments carefully, but unfortunately he couldn't reach the specific formula to be able to show that. In physics, if we can't make something in formula, or we can't, bring mathematics. Mathematics actually is the language of physics. If we can't make it, it's a big loss. But nowadays, we know this formula by Snell's law, which I'm not going to talk about it. After Greek people, Nicholas Copernicus was the person who did a really revolutionary, I going to say, in understanding of the universe. He was living between 1473 to 1543, and in his model, he stopped the sun and set the earth in motion. He tried to make his system in this way. This is our sun, and this is our planet. But, it was a big claim, and definitely some of the scientists at that time were not believing and were not trying to accept, but some were trying to do. Reinhold was one of them who could, write his book. Nowadays, still it's applicable, and he used by what the system that Copernicus tried to show. He tried to write his book, but Tycho Brahe, a very famous astronomer, tried to not accepting it. But he was kind of rich person, and he had his private observatory. So by what Copernicus already said, he could also believe in that Copernicus is right, and planet Earth is not locating in the center of the universe. And also, by his observations, he could reach to two big points that previously Aristotle was claiming that the heavens are unchanging and all natural motion is in circle. But what he observed was a flaring up of a new star. Chris tried to introduce me, and he said that he's studying neutrino oscillations in core-collapse supernova. Actually, what is core-collapse supernova? Supernova. Okay, let me go back to the origin of the name. Super and nova. Nova means the new and the born, right? Previously, the scientists were thinking that this is because of the born of a star. When we see a very shiny thing in the sky, it means a star is just trying to born. But it's actually wrong. Supernova is a fate of, it's the end of the star actually. The fate of all massive stars is just like maybe humans. All will die. And supernova is the end state of a star, which makes a very massive explosion. So he could observe that in 1572. And it was in opposite direction with what Aristotle already said. And again, in the next step, he just tried to show that a comet with elongated orbit. He was just saying that all motions are in circle, actually.
Milad, I have a quick question.
Please.
Over time, when these physicists came up with new ideas that contrasted old ones that have been around for decades or hundreds of years, what was the general feeling like in society? Were these new ideas welcomed? Were they seen as heresy, like going against old beliefs?
Definitely were not believing them, and they were against them actually. And because I will talk about Galileo. He's the very famous guy that the society and of course even the scholars at that time were trying to be against him, but what he was trying to say. But maybe they were lucky also, the media was not that high, at that time, and the scholars were not the same as just, for example, nowadays. So, but yeah, of course it was not so easy to convince them. For example, Aristotle was thinking that, okay, let me ask you a question, when I was just coming, I just took a statue and a chocolate. So of course they have different mass, right? This is heavier than this statue, right? So if I want to, if they are in the same height, and I'm just trying to drop them down, so what do you think? Which one is just reaching to the ground faster? Yeah, please.
I think it's the same.
It's the same.
The one that has bigger mass.
Okay.
The same.
The same.
The same.
The same. Any other idea? And if you say the same, why? And if you say the bigger mass, why? Why the bigger mass is?
I thought that the mass would would go faster because it's bigger.
Okay. And why do you think that they are the same?
I think they're the same because...
Loudly, please. I can't hear you.
I think they're the same because...
Because?
Maybe because the gravitational force compare everything.
Very good. Very good. So, you know about the gravitational force. Okay, great. Yes. But you know that Aristotle was thinking that the object with the heavier, with the bigger mass, will reach or will hit the ground earlier. But Galilei, I'm just going to talk. He said the same. And I will try to explain. But your answer is really great, and I'm really happy by your answer. Actually, the greatest revolution happened at the time of Kepler. And still, his laws are, like the first step for all astronomers and physicists to be able to understand the nature. And of course, he was Tycho's student, and as I said, he tried to use the Tycho Brahe's data and collect them. And after that, he made 3 famous laws, which nowadays we just know them by Kepler's law. I'm not going to explain them in details because it requires mathematics. And maybe you still are not familiar with the mathematics of ellipse and focuses and stuff. But let me explain you in this way. The first law says that all planets orbiting our sun in an elliptical shape. This is ellipse. How can we make an ellipse? Imagine we have just 2 points and there's a rod, and just we take a pencil and we just try to round it. This is how we make an ellipse. This is called ellipse. And these 2 points are called the focus. So he believed that sun is in one of the focuses and the planets are orbiting around sun in these orbits. So this is the first law of Kepler. His second law, again, the sun is in one focus and the planet is trying to orbit. And the length from the planet to the sun in one period. Okay, so line sweeps out equal areas. This area is exactly the same as this area in the same period. This line and this line. This took, for example, 1 month to the planet to come from here to here, and 1 month from here to here. So the area, if we connect these planets to the sun, these 2 areas are the same. And the third law says that the squares of orbital periods are, orbital periods means that time takes that the planet just make a round are proportional to the cubes of the orbital semi-diameter axis. After him, Galilei somehow approved what the Copernicus was trying to say, and he did the first steps of the laws of the motion. And he knew that, he somehow made a very famous experiment, that what I did now, he just went to the Pisa Tower, and this is the object with the heavier mass and the smaller one, and he proved that they're hitting the ground exactly in the same time. But if you want to really to be precise, it's not the same time because of the air resistance. But the time difference is negligible, actually. And that's what exactly he said. It's because of the gravitational force. I don't bring the mathematical formula here, that F of G equals to G, the capital G, which is the constant, into the first body mass and the second one, which is the mass of the Earth. Because the mass of this object with the mass of our planet, this mass is negligible, is nothing compared to the mass of the planet Earth. So both of them are going to be the same. So that's why both of them are going to hit the ground at the same time. Of course, Galileo even at that time didn't know it. Newton proved it by equations. But Galileo also was the first person who did the astronomical telescopes and was looking at the heavens and trying to understand the nature of them. But we do call this guy Ibn Haytham, but in English they call it Al-Hazen. This guy made a big, projects and works on optics. Aristotle was thinking that our eye emits light, and that's why we can see the objects. I just repeat my word. Aristotle was thinking that our eyes emit light. That's why we can see the objects. But he said, no, it's not correct. We see objects by the light scattered from them. For example, I can see you and you can see me because of the scattered lights. And then he constructed the pinhole cameras, and he also studied lenses. But he was not successful to make an astronomical telescope for himself. After him, Newton. I think all of us have heard his name, and he's like a very great and giant guy. And his contribution to physics made people to believe that physics is over. There's nothing left. He just always, he was a great mathematician too, and whenever he couldn't explain some physical phenomena, he was just trying to create a mathematical formula for it, and by that formulation he could just explain these physical phenomena. Binomial theorem, like what we are studying in our, elementary or middle school, like a plus b, and then when this a plus b raised with, square is just a square plus 2ab plus b square, a plus b, then with the power of 3, or cube, is going to be a cubed plus b cubed, 3ab, and blah, right? So these are called binomial theorem, and he did. And in calculus, he made like integration, differentiation, and stuff. Of course, Leibniz, the German mathematician, was in the same time with him, and he was also contributing these things. But Newton is very famous by his understanding in physics. And of course, the law of gravitation. As your friend said, that F of G. He said, what makes this apple to hit the ground or the head of the Newton is exactly the same that moon orbits around our planet. One question. You guys know that the moon orbiting around Earth, right? And do you think that we can see both sides of the moon? I mean, for example, imagine this is just like this is moon. Is it orbiting like this that we can see all parts of the moon?
No.
No? Okay. Just we see just one side of that moon, right? And do you know why is that for? Yeah, please.
It's because the sun is the one that emits. The sun emits the light which reflects on the moon.
Yeah.
And then from there the earth orbits around it, and then since you stay in one place the whole time, you see both faces of the moon at different times. I don't know.
At first you were just correct that, yeah, sun, I mean, the moon is just reflecting the light from the sun. But unfortunately, the second step, it's better to say that we only see one phase of the moon or one side of the moon because of this law again. I mean, it's like the earth is just like pulling and just, like that. They are just like trying to, when I was a child, I was just playing this game, but now I can't remember it. If you remember, just please help me.
Oh, like a tether ball?
Yeah. I'm just,
Yeah,
we're
yeah.
just trying to, then suddenly just.
Oh, yeah.
Okay. But, Newton also tried to explain the behavior of the light. That we know that light behaves like a particle and a wave. And Newton was just trying to make a prism and understand how this light behaves. But after him, as I said, after Newton, people were just believing that physics is just over and it was just type of boring science, that all the questions has been answered. But suddenly, few questions came up, and that made us to reach to the point that we are at the moment, and we call it modern physics or quantum physics. And at the same time, in the early of the 20th century, relativity also, came to the physics and made us to understand this universe much better. And maybe you guys heard about relativity, right? Have you heard about relativity?
Anyone heard of the theory of relativity?
And do you know who was the person was working in that theory?
Albert Einstein.
Perfect. Albert Einstein was doing. And what relativity means? What does it mean? Loudly, please.
I don't remember the full meaning, but
Okay.
I remember that E equals energy.
Oh,
E is equal to energy, okay?
MC squared.
MC squared. Okay. What does that mean?
Energy equals.
Yeah.
I think M means motion. Oh yeah.
M-
But I don't know.
No.
Mass.
M is mass, yeah. And C?
I think it's C means calculation.
Any parents know?
Yeah, please.
It's energy. Energy is mass at the speed of light
Yeah.
squared.
Yes, exactly.
Oh.
Yeah. But before that, it's just can be, Einstein, this is actually the most famous formula in like 20th century. But I want to ask you a question, like, what actually relativity means? You guys heard about like general relativity and special relativity. right? And these two things are different. I'm just going to talk about two theorems specifically, and of course I do understand for even physicists is a very tough topic to understand. It requires non-Euclidean mathematics and many other mathematic backgrounds, but it's easy to explain what relativity is, which I'm going to tell you. Theory of relativity, as I said, has special and general relativity. So in special relativity, we are dealing with two principles. The first, I just wrote them in words, and I'm just going to read it and focus on the words. The principle of relativity says the laws of physics are the same for any inertial reference frame. What does it mean? Again, I'm going to ask. I'm pretty sure that you understood the laws of physics are the same for any inertial reference frame. What's this three words definition? And what the word relative means. Okay, let me give you an example. Imagine there's a train that is going from south to north. Okay, a train that is going from south to north, and two guys are playing ping pong in the train. Okay, so again, a train is just moving from south to north, and two guys are just playing ping pong, and they're just playing, and the speed of that ball is just 2 meters per second to the north and 2 meters per second to the south. Right? They're just playing, right? Okay. And imagine there is an observer. So I said south to north, and the observer is here. What does he see?
The ping pong ball going. I don't know.
What does he see? He sees that the ball that is going from south to north has 32. It means 30 plus 2 meters per second speed. But the one that is coming from north to south, because the train is moving with the speed of 30, has 28 meters per second. It means the measurement of the motion is relative to the position and velocity of the observer. That's the relativity. Relative. And the second principle is the speed of light. The speed of light in a vacuum is the same for all observers. Do you know how much is the speed of light?
It's in Japanese, but I don't have
It's...
Would Kimika know?
Yeah, definitely she knows.
Kimika, high school student from Kais.
3 times 10 to the 8 meters per second.
3 times 10 raised to the 8 meters per second. And I'm going to explain about some interesting things that we know from the relativity. Time dilation. Do you know that the time will pass slower for someone that is trying to travel with the speed of light? Imagine, instead of just riding the car, we are just on a particle or on something that its speed is 3 into 10 raised to 8 meters per second. So, at that time, the time goes slower. If compared to the person that is just looking at you, or isn't it? And the length contraction. When objects appear shorter, the faster they are moving in relation to the observer. Time and gravity. When the gravity is a lot, is huge amount of gravity, time goes slow.
Can you give an example of that? Like, do we see that anywhere,
Yeah, exactly.
either on Earth or in the universe?
You know, for example, sun, right, is a very heavy object. And imagine we are just trying to pass, you know, this nearby sun. So at that time, yeah, the time is this. And you know, there is a joke in physics community in Japan that they are saying that in Japan the gravity is not that strong because time flies in Japan, you know. Yeah. Simultaneously with Einstein, his colleagues and the other physicists were trying to understand the structure of matter. Sir William Crookes was the person who was trying to understand the structure of matter by doing a very famous experiment. What he did, he was trying, you know, he just had a. Have you studied about this experiment before?
Have
Yes?
you seen this? Yeah.
Kind of, but I don't know what it means.
Okay. So, you know, this is a very high voltage source. The voltage is so high, and we are trying to connect them to the cathode and the anode in a vacuum. And he tried to see what happens. You see that the rays are emitting from cathode part to the anode. And then he, of course, announced this result to the other scientists and other physicists. So they tried to put a wheel here. And they saw that the wheel is just rotated. And they were wondering whether they are electromagnetic wave or not. Who knows what's electromagnetic wave?
I don't know.
What's an electromagnetic wave?
It's like a magnet being on and off.
Sorry, come again.
A magnet like being on and off.
No. Electromagnetic wave. Yeah, please.
Magnetism caused by electricity as in batteries.
Louder, please. I can't hear you.
Yell at him.
Magnetism caused by electrical materials like batteries.
Okay, so we can just explain in this way also. The waves, you know, electromagnetic waves, the waves that have electrical and magnetic fields. Electromagnet, right? So even the light, you know, the examples are just like radio waves, X-rays, lights, gamma rays, and so it depends on the frequency. So they were wondering whether they are or not, and whether they are charged particles or not. Do you have any suggestion how to understand whether they are charged particles or not? It's very easy. The scientists were wondering whether these particles that are trying to move this wheel, whether they are charged particles or not. How did they understand whether they are or not? Very simple. By just using a magnet, right? If you put a magnet, just you can see that, you know, the behavior changes. Okay, I asked you already this question. And the next is the female that she contributed to physics. And she got 2 Nobel Prizes in chemistry and in physics for her work that made her to discover polonium and radium. And of course, she could explain the effect of radioactivity and the radioactivity decay. Okay, one question. Who knows what's radioactivity? Any?
Do you know from the glasses?
Yeah.
Tell them.
Do I have to?
What's radioactivity?
It's like energy coming off of an object, a natural object. Actually, it could be both. But, it comes from like, it's so hard to explain that.
Okay. Who knows what's isotope?
Isotope?
Yeah. Yeah, please.
What do you have when an element has more neutrons than
A bit loudly and slowly, please.
when an element has more neutrons than a proton?
Exactly. So, the atoms that have same number of protons and electrons, but different neutrons. They say they are isotopes of, like for example, hydrogen or helium. Okay, so isotopes, some of them are very, stable. I just can't call them stable. And some of them are not. Those unstable isotopes are they radiate. Okay, and then we call it radioactivity. They radiate, and they make the radiation. And this picture might be a bit difficult, but I wrote them in, verbs also. We have 3 different types of radioactivity: alpha, beta, and gamma. Alpha decay is when there are too many protons. Here. Imagine there are too many protons, so the emission is going to be positive charge. And in the case that we have too many neutrons, negative charge is going to decay. And when there are just huge amount of energy, gamma rays are gamma radiation is gonna come. So we call them as alpha, beta, and gamma. J.J. Thomson, a great physicist and a very famous one, and he was believing that atoms must have internal structure. Okay. Of course, we know that atoms have internal structure, and we know the 3 basics of them, right? What they are? Internal structure. I just told you guys. Electrons. What are the more 2? Protons and neutrons. Okay. Electrons are negatively charged, right? How about protons? Protons are? Someone is saying positively, but it's not loud. Yeah, positive, of course. And neutrons are? Neutral. Neutrons, neutral, right? Okay. But he was believing that they are all kept in a plum pudding model. It's like the negative parts are like these plums, and the positives are distributed. He was believing that the structure of atom is like that. But after him, Rutherford came, and of course he was one of the pioneers of the nuclear physics and the radioactivity. And of course, also one of his great jobs were discovering proton. And also he tried to explain the inner structure of an atom, that protons and neutrons are at the core, and the electrons are orbiting around it. But after him, a Danish scientist, Niels Bohr, came and just slightly corrected Rutherford's theorem, and he said that atoms are like different planets, they are in different orbits. Electrons are orbiting around the nucleus. But Rutherford were believing that all electrons are in the same orbit. So orbitals was his job. Photon and light. Photon is a quantum of electromagnetic radiation. Who knows what's the meaning of this quantum? I already said what's electromagnetic, wave or radiation. So what's the meaning of quantum? You guys may hear about quantum mechanics, quantum physics, and these stuffs a lot. What's quantum actually? Do you have any idea?
Anyone?
Quantum is actually the plural of quanta. What that quanta means.
Yeah, you don't just say it out loud.
Yeah, please.
Super small.
Super small, perfect. Yes, it means a unit. That we can't break it even smaller.
So smaller than an atom.
Exactly. So lights have the wave and particle behaviors. We already, and many scientists try to explain the wave behavior of the light, but the particle behavior, if we want to show, is by just trying to say that the light is emitting, in order of units. And that's quantum. Photons have zero mass. They're really massless. And they have no electric charge, and they are subatomic particles, actually. And they interact with matter. What does this mean? I got a question from one of the students that what Einstein is famous for. So Einstein, of course, is famous for his theory of relativity and his experiment in photoelectric effect. And actually, he didn't get Nobel Prize because of his theory of relativity. He got the Nobel Prize because of photoelectric effect. Because the theory of relativity is still, until last year was in doubt because they couldn't detect it. But photoelectric effect, what happened, again, almost the same experiment as Crook did, but here he tries to emit light, and he saw that photoelectric effect, that when we radiate photons, electrons are just going to move. And so when we emit these photons to this plate, electrons are emitted. So that's what we call photoelectric effect. So it means photons are interacting with matter. That made a new story and new field in physics, which we call it quantum physics.
Isn't that how a solar panel works as well?
Yes. And even nowadays, we are trying to, even, the particle accelerators and stuff. I will explain briefly about it. Quantum mechanics. These guys, Schrödinger and Schrödinger cat, might be very famous for you guys. But these equations I'm not going to explain. Of course, what he did in quantum mechanics is exactly what Newton's laws of motion tried to explain. And it's a branch of physics that works, that what's actually inside the atoms. For example, in classical physics, we just trying to explain, for example, one question, if a car is trying to go from Tokyo to Kyoto, for example, and with a speed of 60 kilometers per hour. And if you know how long is the distance between the Tokyo and Kyoto, it's so easy for us to understand how long does it take by easy calculations like velocity equals to displacement over time. That's easy. But how about the particles? When they want to travel, how can we measure and how can we calculate the dynamics of it? Elementary particles. As I told you already in my talk that photon is an elementary particle, or it's believed that, or with our knowledge, that elementary particles doesn't have any, smaller particles. So now we believe that these elementary particles don't have anything smaller than them. And this is called the standard theoretical or the standard model in particle physics, actually, that these part is different with these greens and the red one. So there are quarks, leptons, and gauge bosons. Definitely understanding about these particles gave us a better understanding of the universe. Today I'm not going to talk about these things in details because it's going to be a bit more complex and we don't have enough time, of course. Just for some example, I just can say a proton is made up of 3 quarks, 2 up and 1 down. But neutron is vice versa, 2 down and 1 up. These particles itself are made of these things. And understanding the subatomic particles, like neutrinos, neutrino oscillations, my topic that I'm currently doing, in core-collapse supernovae, neutrinos are playing a key role in the explosion mechanism of the core-collapse supernovae. They make that explosion. And they are in different flavors, electron, muon, and tauons. Understanding the particles is giving us a bright understanding and, how can I say, understanding of the particles can give us a better understanding of the universe, because we believe that universe is made up of these particles. Our understanding of astronomy or astrophysics is not like what our ancestors were trying to do or just by observing. How these subatomic particles behave and how they are trying to help us to understand what our universe is made of. And also, understanding these subatomic particles is making some advances in technology for us. Particles accelerators. You might hear about CERN, and like in Japan we have the Spring Gate, J-Park, and KK. And I was doing my research for 2 years at KK in Tsukuba, which the synchrotron radiation experiments in X-ray physics group we were conducting. What's synchrotron radiation? It's quite simple. I can say that there's a filament, and they are trying to hit that filament, and an electron is just released. And there were big size of the magnets, like the same size of this building, were there. And those big, magnets were just in that circular, in particle accelerators, we have, 2 types, like circular and the straight one. In circular one, that we were just doing our experiments, those magnets, when an electron is in a very big magnetic field, it's trying to accelerate. And it speeds up almost the same, speed of the light. And suddenly, it's like a car when you, for example, just trying to turn, for example, left to right, you have to, lower your speed. So then, that's, when it's just trying to turn left or right, it emits some radiation. And we were just detecting, for example, a specific like wavelength, for example, X-ray. Just we were in X-ray physics group, and then we were trying to understand, for example, at that time, the Fukushima Daiichi's, the rice. They were just trying to check whether the cesium is in those, rice or not, and whether they are healthy for our body or not. And of course, particle accelerators are also helping us to understand better in medicines and in biophysics. And understanding modern physics helps us to get better and more precise telescopes. And yeah, what is gonna be the next, no one knows, and we hope that our efforts about understanding the universe one day will let us know and understand where do we come from and what's gonna be the fate of all of us. In physics, we do believe that what we call the beginning is often the end, and to make an end is to make the beginning. And end is where you started from. Thank you very much.